Hello, my wonderful students and chemistry lovers. Today I'm going to talk to you about how to calculate lattice energies using Born-Haber cycle. My name is Dr. Lotano Kwesili, and I'm going to serve as your guide today in this interesting lecture and conversation, okay? Recall in the previous lecture videos when we talked about ion-to-ion interaction, we laid emphasis on what we call the lattice energies. And we talked about lattice energy being a measure of the strength of different ionic bonds and different ionic compounds. And we were able to define lattice energy as the amount of energy released when gaseous ions combine to make 1 mole of an ionic compound. However, these particular lattice energies involved in the formation of ionic compounds are usually difficult to measure directly. However, we can calculate them using a mathematical model known as the Born-Haber cycle. The Born-Haber cycle helps us to trace the different amounts of energies that are involved in the different reaction steps as those combining elements are taken from the elemental form to the gaseous form and ultimately to the formation of their ionic compounds. So what we are trying to say here is that the Born-Haber cycle allows us to know the full story as to the stepwise process, the energies of different steps, okay, as elements react or combine to ultimately form ionic compound. And of course, the Born-Haber cycle is essentially what we call the Hess law applied to the ionic compound. So if you watch now, we are bringing in another dimension or body of knowledge. We're talking about Hess law. So we have to establish what Hess law is all about. That will give us a footing, an anchor to now be able to appreciate what the Born-Haber cycle is and how to apply it in calculating different lattice energies of different ionic compounds. Okay, so what we know as Hess law is also known as what we call Hess law of constant heat summation. All right, and this particular law tells us that the heat either absorbed or evolved or released in the course of a chemical reaction, that heat that is either absorbed or released in the course of chemical reaction is known as enthalpy change or heat change, delta H. All right, so according to Hess law of constant heat summation, the enthalpy change, the energy dispensed, the energy involved, either being absorbed or released in the course of any chemical reaction, is a fixed quantity. It doesn't change. And this is independent of the path that the reaction took to get to completion, or irrespective of the fact that some reactions proceed in different steps, and each of those steps involve different energies. Put in simpler terms, reactions are usually depicted using a chemical equation, which is a sum of all the reaction steps that we cannot see that actually happens in the course of a chemical reaction. However, each of those reaction steps has certain amounts of energy that are either absorbed or released in the process. Okay? So we cannot measure all of these directly. However, the Hess law helps us to understand that those different reaction steps involving different enthalpy changes or energies being absorbed or released, we can be able to calculate or sum up all those energies involved in the different individual steps, and that should ultimately equal the amount of energy that was dispensed or that was involved had it been the reaction proceeded only in one step, involving elements in their standard physical state. So this is what we say. So again, according to Hess law, or what we call Hess law of constant heat summation, the amount of heat either absorbed or evolved in the course of any reaction, that is the enthalpy change, delta H, is a fixed quantity, irrespective of the fact that the reaction would have ultimately happened between elements in their standard state, of course, in one-step process to form the ionic compound, or the compound as it were, or there's possibility we would have been able to study this reaction in terms of the series of individual steps that are involved. having in the at the back of our mind that each of those individual steps has certain amounts of energy content, energy that is either absorbed or released. That's the enthalpy change for each of those steps. So if the reactions proceeded in different steps, it behooves on us now to be able to add up the different enthalpy changes or the heat changes involved in all those reaction steps. And we should expect the amount of the heat changes or the enthalpy change involved in those reaction steps to equal the same amount of energy, which could have been measured directly had it been the reaction proceeded only in one step. So that is what the Hess's law of constant heat summation is talking about. So the mathematical model that helps us to express the Hess's law, okay, is that the standard heat of formation, this is the standard enthalpy of formation, okay, is equal to sigma delta Hn. Of course, this shows this n is telling us the possibility of different steps. So if the reaction, the enthalpy change involved in the reaction, if it only happened in one step, should equal when you sum the enthalpy changes of the, of the reaction steps, had it been the reaction proceeded in the several steps. So this is what we are saying here. So where delta H standard is equal to the standard enthalpy of formation, that is heat absorbed or evolved if the reaction happened between elements in their standard phase state just in one step to give us the ionic compound. But however, if the reactions are broken down into different series of steps, as we have expressed in the Born-Haber cycle, okay, or according to Hess's law, the sum of the heat absorbed or evolved, the enthalpy changes of the different steps, okay, is what we have if we have sigma delta Hn. That is the summation of all the enthalpy changes for all the individual steps. It should equal to the standard enthalpy of formation had it been the reaction proceeded in only one step involving elements in their standard physical form or state. This is beautiful. From all of this, you can now begin to appreciate the idea of conservation of energy. Remember, I told you, the whole entirety of what we do in chemistry is to study matter. Okay? And whenever we are studying matter, we cannot study matter in isolation. Whenever you play around matter with energy, with heat, you're going to have them change from one form to another. All of this is what we did when we were introducing this topic. You can go back, refer to some of those videos. So from what we have seen here, there is a conservation of energy. All right? Irrespective of the fact that reaction could proceed in just in one state, involving elements in their standard form, or we can break down those the reaction steps into individual steps. And at the end of the day, the two energies are conserved, or the amount of energy is conserved. And that is because of the first law of thermodynamics, which tells us that energy can neither be created nor destroyed, even though they can be changed from one form to another. So suffice it to say here that Hess's law is a consequence of the first law of thermodynamics. And because Hess's law, when applied to an ionic compound, is known as the Born-Haber cycle, it is important to state clearly here that the Born-Haber cycle is an expression of Hess's law applied to ionic compounds. So when you want to calculate the lattice energies involved in the formation of ionic compounds, applying Hess's law, you have the Born-Haber cycle, which is what we are introducing today. All right? And this is interesting. So hence, you can agree with me now, since we are talking about ionic compounds, you can agree with me that Born-Haber cycle, which is the expression of Hess's law to ionic compounds, is now the mathematical model, okay, which we now use to treat energies associated with the different steps that elements get involved in as they change from their standard forms to the gaseous ions, and ultimately till they form what we call ionic crystal lattices, or till they form their ionic compound or salt compounds, as it were. Again, to repeat myself for emphasis, when we talk about Born-Haber cycle, I told you this is a mathematical model applying Hess's law that helps us to be able to determine the different steps, the enthalpy changes involved in the different steps as standard elements combine to make an ionic compound. All right? And this is very, very important. And of course, those standard elements will not just ultimately, form ionic compound without going through certain processes. One of the processes is atomization. One of the processes is that we have to change sublimation. We have to change standard solid matter, of course, to a gaseous phase, getting it more very reactive, more unstable, eager for it to, follow up on some other steps of the reaction. All of this will make more sense as we move down. Okay? So the Born-Haber cycle is what will help us to treat the different enthalpy changes or energies associated with the different steps that happen as we, begin to change standard elements in their standard physical states as they begin to combine, of course, change into gaseous ions, which now ultimately are held together by strong electrostatic forces to make their ionic crystal lattices or ionic compounds, as it were. I believe it's making sense. If that is clear, we're going to consider the reaction between our two model elements, which is sodium and chlorine, to make a model compound known as sodium chloride. Again, recall that sodium has one electron extra that it can give out to become an ion. So it is very unstable, very reactive. The same way chlorine requires only one electron to get, is a redox reaction to gain from the sodium and of course become an ionic compound. Because we are moving from elements of high energy, very unstable, very reactive, to now making a compound that is lower in energy or stable, that means certain amount of energy was given out. So this reaction again is known as an exothermic reaction. And what we have now is the negative enthalpy, delta H. The heat change here is negative value because we started with particles of higher energy and we're ending up with a compound, an ionic compound of lower energy. The reverse would have been the case if we are doing dissolution or breaking up of sodium chloride. Okay, that means we need to supply heat into this system. Okay, and when heat is being supplied into the system, we are doing an endothermic process because that way the reverse of this reaction is now we are going from a subparticle of a compound of a low energy to particles of high energy. That means heat was taken in because you're going in from lower energy to higher energy. That means heat was absorbed. So the reverse of this is going to be an endothermic reaction, which is what we see if we decide to dissolve this in water or we try to break up this ionic crystal lattice or ionic compound. This is beautiful. So from here, you understand that this is an exothermic process and we're looking at a negative delta H value. So the delta H value here, if we are dealing with elements reacting in their standard states, the standard state of sodium is solid. If we didn't change it to the gaseous ion, okay, so we're just giving an overall reaction that tells us what happens, how sodium chloride is formed. But this is not the full story. The full story is that this reaction proceeds in series of steps. Series of steps. And that series of steps and the associated energies is treated when we use what we call the Born-Haber cycle, which is Hess law applied to ionic compounds. So, but if we are looking at this particular equation, we are not getting the full story. Because looking at it critically, you understand that when you are talking about lattice energies, you are talking about gaseous ions combining to make 1 mole of an ionic compound. So, in balancing this equation, we must have 1 mole here, 1 mole. It must be 1 mole if we are talking about lattice energies. So you see, we cannot touch here if we're trying to balance this equation. So the only way to balance this equation is to put the coefficient half in front of chlorine gas. Chlorine is always a diatomic gas. Therefore, we only need 1 chlorine atom in its gaseous phase to combine with 1 sodium metal to make 1 mole of sodium chloride. So that's why the coefficient here is half, telling you that this covalent bond here was broken. Now, if you pay attention to this overall reaction, you cannot say when and how, at what point was this covalent bond broken. But if you understand Hess's law applied to ionic compound, talking about the Born-Haber cycle now, you can be able to understand in the 5 key reaction steps, at what point was this covalent bond broken and which amount of energy was associated with the breaking of that covalent bond. In some other instances, this sodium ion will be changed into a gaseous sodium atom. This sodium atom in the solid standard state will also need to be changed into a gaseous ion, because in getting it from solid to gaseous ion, you are getting it more very unstable and eager for the ionic reaction to happen, for the reaction with chlorine atom to happen. So these are things that this particular reaction in this particular one step or in this particular equation doesn't tell us. However, if elements in their standard states react, of course, to give us ultimately 1 mole of sodium chloride, as you have it here, such reactions that proceed in one step involving the standard states of the individual constituent elements can be measured directly, no problem. It can be measured directly using a device known as what? A calorimeter. And when the standard heat of formation or the amount of the enthalpy change of this reaction involving sodium in its standard state and chlorine gas in its standard state to give us 1 mole of sodium chloride, this enthalpy change or standard heat of formation can be measured directly with using a calorimeter. And of course, the value is given as negative 411 kilojoule per mole sodium chloride. So the standard heat of formation involved when elements sodium metal react with chlorine gas to give us 1 mole of sodium chloride is the standard heat of formation, or what is also known as the enthalpy of reaction, delta H Rxn, which is given and measured, can be measured directly using a calorimeter, is negative 411 kilojoule per mole sodium chloride. However, this doesn't tell us the full story, because this reaction actually proceeds in 5 important steps. So for us to capture what happens in those 5 important steps, we are going to beam our searchlight to understanding what we call the Born-Haber cycle. As a matter of introduction, we're going to describe these 5 steps and how it happens. It's going to also help us not only understand how these things happen, it's also going to help us to define the key terms that we use when we are studying thermochemistry and thermodynamics in physical chemistry. And some students struggle with some of these. But if we're able to understand these 5 important steps in the formation of ionic compounds as described using the Born-Haber cycle, it's going to make more sense, because in the next lecture video, I'm now going to show you typical examples of the Born-Haber cycles and of course how to use them to calculate the lattice energy ultimately of different ionic compounds as they are formed from their individual elements. Okay? This is nice. So, however, the Born-Haber cycle now breaks down this overall reaction into 5 important series of steps. Okay? And we're going to take them one after the other. The first step here is the sublimation of a mole of sodium metal into the gaseous sodium atom. So here you have sodium metal in the standard physical state is solid, but we have to first of all change it to a gas, because changing it to a gas is more or less preparing it for the ultimate reaction with chlorine atom when the covalent bond here is also broken. So changing it to the gaseous phase is more or less preparing it, getting it more energized, because gaseous particles have more kinetic energy, they are more reactive, they are eager to lose their electrons, because one of the things you need to know about metals is that the metallic character property is as a result of them to readily, lose their electrons. For non-metals, they readily gain their electrons. All of this is to ionize them, ultimately. So moving sodium metal in the solid state to a gaseous phase is the first step. And if you are changing something from solid straight to gas, you are doing what we call sublimation. So that's why we say sublimation of 1 mole of sodium metal, which is in the standard state, into sodium atom, which is in gaseous phase. So ultimately, we are looking at changing this into sodium metal in the gaseous phase. Okay? That is what happens in the first step. So in the first step, we take on the first element, okay, change it into a gas by sublimation. And the enthalpy change, every reaction step requires certain amounts of energy involved. Energy is defined as the ability to do work. So for every reaction or reaction step to happen, there's certain amount of energy content that is connected to that particular reaction step. That is ultimately known as the enthalpy change, or the heat change involved. And that heat change could either be energy that is absorbed or released in the course of that reaction step. So in doing this, in changing this from the standard state to the gaseous phase, it's still sodium metal atom in the solid phase. We've changed it to the gaseous phase. In doing this, we are doing sublimation. And the enthalpy change, the heat change involved in that reaction is delta H SUBL. That is enthalpy of sublimation. That is the enthalpy change, or the enthalpy or the heat change involved when you are changing 1 mole of a solid, metal atom into 1 mole of a gaseous metal atom. This is clear. So the heat change here, the enthalpy change here in the first enthalpy change is what we call the heat of sublimation, or enthalpy of sublimation. Now, because we are dealing with moving this from the standard solid state to the gaseous phase, we are talking of sublimation. However, in certain other reactions, this could be in the liquid phase, and you want to gasify it, you want to change it into the gaseous phase. Of course, in that case, the delta H will now be, associated with vaporization, because vaporization involves moving something from the standard liquid state, of course, to the gaseous phase. So had it been this is a liquid phase and we gasify or change it into a gas, of course, it would have involved, the enthalpy change would have been delta H VAP, which is enthalpy of vaporization. But because we are doing sublimation here, the heat change in the first step is enthalpy change, or enthalpy of sublimation, or heat of sublimation, as the case may be. I believe it's clear. So the first reaction step, we're dealing with the first element, or the first reactant. In the second step, we move to the second reactant, which is chlorine gas. It's a diatomic molecule. Now, what happens here is that if you look at it, we are dealing with 1 mole of sodium chloride. That means we only need 1 atom of chlorine in 1 mole of sodium chloride. So therefore, since this is half of this, we need only half of these 2 chlorine atoms in 1 molecule of this chlorine gas. Since we just need 1 of it to react with this to give us this, that means the covalent bond, that's covalent bond joining chlorine atom to the second chlorine atom, has to be broken. Energy is the ability to do work. Certain amount of energy is released or required to break up this covalent bond. Okay? And that particular energy is called the bond dissociation energy. So the enthalpy change in the second step, and the second step involves breaking of the covalent bond between the chlorine atom and chlorine atom in diatomic gas of chlorine. So breaking of the covalent bond, the chlorine to chlorine covalent bond, okay, to make 1 atom, or to make atoms, okay, 2 atoms of gaseous chlorine atom. So remember, the chlorine gas already is in the gaseous phase. So we're not talking about changing them to the gaseous phase. Rather, we're interested in breaking up the covalent bond to make a monoatomic gas of chlorine, because that's what we need. We just need 1 atom of chlorine to react with this to give us 1 mole of this. So in the second step, it's all about the enthalpy change, the energy required for us to break up the covalent bond, and that is known as delta H BDE. Because we are dealing with half atom, the amount of energy that is released per chlorine, monoatomic chlorine gas atom is now half delta H, okay, BDE, which is the bond dissociation enthalpy, or bond dissociation energy, or bond energy simply. All right. Again, this particular step is dicey. It's dicey because there's another term we normally use to be able to describe this phenomenon, or what is happening here. And that term is called enthalpy. Enthalpy of atomization. Enthalpy of atomization. What is enthalpy of atomization? Here you are talking about heat change involved when we break up 1 mole of a covalent bond to make, okay, atoms of that particular molecule in its gaseous phase. Okay, So the amount of energy involved in breaking of this covalent bond means you are changing it from the molecular form, to atomic forms, even in the same gaseous phase. Okay, that amount of energy involved in breaking up the covalent bond in a molecule to make atoms still in the gaseous phase is known as enthalpy of atomization, which is also what we call the bond dissociation enthalpy. I believe it's clear. So in the first step, again, we change sodium metal in the solid form to gaseous phase. In the second step, we move to the next reactant, yank off and break off the covalent bond between the two chlorine atoms for us to get the different atoms of chlorine still in the gaseous phase. That's what we do. The amount of energy released here is known as the enthalpy of or the bond dissociation enthalpy, all right, or the enthalpy of what? Atomization. The amount of energy required for us to break up the covalent bond to give us gaseous atoms. Okay? Fantabulous. So when we are done with this in the second step, we revert back to what we made in the first step. And in the first step, we made sodium gas, sodium atom in the gaseous phase, which is now very energized because gaseous particles have more kinetic energy, is eager to do what metals do. What metals are known for is that they readily release their valence electrons for them to change into an ion. Ultimately, what we need at the end of the day is ions to have electrostatic attraction, of course, to give us an ionic compound. This is key. So in the third step, we revert back to what we made, the product of the first step, which is sodium metal in the gaseous phase. And what does metal do? Metallic character is all about readily losing your valence electron to become, of course, when it loses its valence electron, you are going to now have sodium ion, and of course, it releases electron, okay? And remember, electrons, when they are released, don't go into the vacuum. Remember the conservation of matter. The same way you remember the conservation of energy. Matter can neither be created nor destroyed. Electrons can neither be created nor destroyed. So there's a redox happening here. If sodium gaseous atom loses its electron, therefore something somewhere, in this case, the thing we made in the second step, the chloride atom in the gaseous phase, is ready to accept the electron and also ionize. Okay? Now, but in the third step, again, we are doing ionization because now the sodium atom in the gaseous phase now loses one electron, of course, to the chloride atom in the gaseous phase, and losing the energy, okay, involved or released when a sodium when a metal atom in the gaseous phase loses an electron is known as the ionization energy, IE. So the enthalpy change in the third step is ionization energy. Because we are dealing with sodium that ionizes by giving only one electron, it doesn't have the second ionization energy like we have in magnesium and calcium. That's why we have delta, the energy enthalpy change here is just IE. Okay, it could have been IE1 and delta H IE2 if we are dealing with elements like magnesium or calcium that have two electrons to give out in their valence shell to ionize. This is nice. So then the third step is all about ionization, changing the sodium metal in the gaseous phase into an ion by loss of one electron. Again, now in the first step, of course, the energy associated with this is called the ionization energy, in which case we have only one ionization energy here. So in the first step, what happens is that in the first step is that, of course, the chlorine atom in the gaseous phase now captures, all right, this chlorine atom now captures this electron, okay, now combines with that electron that is being transferred to it from the sodium metal in the gaseous phase, okay. It now captures that electron, and that ultimately changes chlorine atom to what? To chloride ion. Changes chlorine atom, 1 mole of chlorine atom to chloride ion. And of course, again, this reaction step has an energy content. There has to be an enthalpy change. There has to be energy involved in that. And recall from our basic understanding of inorganic chemistry, we understand that the energy either absorbed or released when a gaseous atom accepts or gains, or an electron is added to a gaseous atom, is known as the electron affinity. It's known as the electron affinity. So in the fourth step, the chlorine atom gas, okay, monoatomic gas that was made in the second step, in the second step, now captures the electron, which is what happens in electrovalent combination, which is what we know in ionic combination, transfer of electron from a metal to a non-metal. At what stage does it happen? You see that this overall reaction doesn't tell us that. But using the understanding of Born-Haber cycle, we can now tell that transfer and capture happens in the third step, where there is ionization of the metal. And of course, the capture of the electron happens in the fourth step, where of course the chlorine atom now captures the electron, combines with it to make a chloride ion. And that energy, that is involved, energy, the enthalpy change involved when the gaseous atom accepts or gains an electron, and an electron is added to a gaseous atom, is known as the electron affinity. So in the fourth step, the energy, the enthalpy change, or the energy involved, or the energy content of that reaction step is delta HEA, which is what? Electron affinity. We use 1 because there's only 1 electron that is involved that was captured. It could have been 2 if we are dealing with electrons being captured, more than 1 electron being captured in the process. This is fantastic. So it's important to recall that electron affinity is the energy absorbed or released, of course, when an electron is added to a gaseous when an electron is added to a gaseous atom. Pay attention to this. Ionization energy involved or absorbed or released, of course, when electrons are lost from a gaseous metal atom. So the metal atom must be in gaseous phase. That was why we changed it from the standard solid phase first into the gaseous phase before it now ionizes to give us the ionization energy. Again, we changed this already in gaseous phase, but we're able to atomize it. The heat of atomization was involved, changing it to an atom. And because it's an atom in the gaseous phase, when electron is added to an atom in the gaseous phase, the amount of energy, the energy content, the enthalpy change there is now called electron affinity. Of course, we are dealing with non-metal because these are those elements that now accept electron from the metals which readily loses electron. This is beautiful. So all of these things we are describing was not explained to us by merely looking at the overall reaction. So even though we can be able to determine experimentally using a calorimeter the standard heat of formation of this reaction, Born-Haber cycle helps us to show the different steps so that we can be able to now use theoretical value. There is a table that captures the different enthalpy changes for any of these happening. So when we're able to get all the enthalpy changes involved and look at our standard tables that give us all the enthalpy changes for all of these processes, if we add it up, at the end of the day, the enthalpy change, okay, or the summation of all the enthalpy changes should equal to that particular standard heat of formation that we're able to measure experimentally using a calorimeter. This is what we are talking about, and that's what Hess's law is talking about. So in the last step now, since we have been able to make sodium ion, and again this accepts electron, the chloride ion, the chlorine atom accepts electron and now becomes chloride ion from the metal, now becomes. So we have made sodium metal and we have made chloride. We have made sodium ion, okay, in the third step, and we made chloride ion in the fourth step. So if you have the opposite charges, they're just going to be an electrostatic attraction force that now combines, that now allows sodium ion, of course, to combine with chloride ion. All of these is in gaseous phase to now give us sodium chloride, which is, of course, solid and a crystal. And at the same time, certain amount of energy is given out, which is the lattice energy. I believe you understand it. So in the fifth step, the two ions that are made, which are in gaseous phase, they are very unstable, they are very reactive, they have high kinetic energy. They are eager to combine so that they can make substance that are in solid form, which is lower in energy. All right. And of course, release energy in the process. So what happens is that when 1 mole of the sodium chloride is formed, it simply happens because 1 mole of sodium gaseous ion combines with 1 mole of chloride gaseous ion that were made in the previous steps to give us sodium chloride. And the amount of energy released in that process is known as lattice energy. That is the energy released when 1 mole of an ionic compound is formed by combining free gaseous ions. Okay? And this is beautiful. So at the end of the day, the energy content or the enthalpy change involved in the last step, which involves the now ultimate formation of the sodium chloride, is called delta H lattice of sodium chloride, which is the lattice energy of sodium chloride. So according to the Hess's law, whether the reaction was determined experimentally using a calorimeter in a one-step process, which doesn't tell us the full story, or we use the Born-Haber cycle because we are dealing with Hess's law applied to ionic compound to break down all of these in the reactions, different reaction steps. If we're able to capture the reaction steps involved using the theoretical table, the standard table that gives us all the enthalpy changes, the values of all the enthalpy changes for all of these possibilities, if we're able to add them up from step 1 to step 5, add it up, it should be able to equal the same amount of heat of formation that we captured using a calorimeter. This is because, again, that the Hess's law is a consequence of the first law of thermodynamics, which states that energy can neither be created nor destroyed. So we're talking about the conservation of energy. All right? The entire thing we do in chemistry is to study matter. You cannot study matter in isolation. You must study matter in relation to energy. So today, what we are talking about is the energetics of ionic compounds. Okay? And for us to study the energetics of ionic compounds, we have to use what we call the Born-Haber cycle. And Born-Haber cycle is an expression of what we call the Hess law applied to ionic compounds. So the Born-Haber cycle, in summary, is a mathematical model that helps us to understand the enthalpy changes that happens in the different steps as an ionic compound or crystal is being made from their individual elements combining, of course, changing into gaseous ions and then ultimately forming the ionic compound. So treating the different energies associated with the different steps in the formation of ionic compound as they change to gaseous ion and ultimately being held together by electrostatic attractive forces to make the ionic crystals is what we call the Born-Haber cycle. That mathematical model is known as the Born-Haber cycle. I believe today we're able to revisit what we mean by lattice energy. We're able to also understand that lattice energy in most cases cannot be determined directly. However, if we pay attention to the Born-Haber cycle, it helps us to break down the formation of ionic compound into important reaction steps involving different enthalpy changes, and that the summation of those different enthalpy changes should give us a value equal to the standard heat of formation, which we would have measured directly if we were using a calorimeter, as it were. In the next lecture video, I'm going to bring out the examples of Born-Haber cycle structurally so that you look at it and understand how to calculate the lattice energies of different ionic compounds using the Born-Haber cycle. All of what we did today is more or less introductory, and one of the ideas is to make sure we understand the key terms involved in thermochemistry or thermodynamics whenever we are doing studies of enthalpy and enthalpy changes. Okay? And in summary, today we understood that the Born-Haber cycle breaks down the formation of sodium chloride into 5 important steps. The first important step and each of these steps has to do with different enthalpy changes or heat changes. The first steps involve the heat of sublimation, and the second step involves bond dissociation enthalpy. The third step involves the ionization energy. The fourth step involves the electron affinity, and the fifth step involves the lattice energy. The summation of all these energies or enthalpy changes will ultimately equal the energy or heat of formation, the enthalpy change or heat of formation or heat of reaction of that reaction had it been we use the calorimeter to measure it in a one-step process involving the elements, the constituent elements in their standard physical states or forms. I believe this made sense to you. Take this as a way of introduction. All of this is to make the ground very smooth for us to kick off. So in the next lecture video, we take it to the next level and we look at examples of the Born-Haber cycles and use it to calculate the different lattice energies that we have for different ionic compounds. All of this we're going to do before we move into discussing issues around covalent combination of bonding. I believe you learned something. If this made sense to you, kindly share this video so that you can get to those students who are struggling with this aspect of physical chemistry or thermochemistry or thermodynamics. Okay? When you do this, you are encouraging me to do more. And of course, you are getting people who are enchanted about the subject of chemistry to begin to understand that chemistry is actually not supposed to be a do or die. It's not supposed to be a fight. It's supposed to be something we learn, in a fun way, in an incredible and easy way at the same time. I believe it made sense to you. If you learned something about this lecture, kindly like, comment, and share, okay? So that you can get to those students who actually need some of the information we're dishing out. I remain your humble friend, Dr. Lattice personally. Until the next time, stay safe and stay away from trouble, okay? Bye.